Back at the beginning of the semester, we described chemistry as the study of matter and the changes it undergoes. But those changes can't occur without energy. Essentially, energy makes things happen. Any kind of process, whether it's physical or chemical, requires energy. Either the energy will be needed in the process or energy will be produced in the process. To launch the space shuttle into orbit requires energy, which comes from the rocket fuel. To turn the turbines on those giant windmills out on the delta, energy comes from the wind. And living things like this Olympic athlete need energy in order to lift those heavy weights. There are two basic types of energy. The one you're probably the most familiar with is kinetic energy. Essentially, kinetic energy is just energy of motion. Any object that's moving has kinetic energy. Kinetic energy depends simply on two things: how much mass a particular object has and how fast it's moving. A bullet fired from a gun has a lot of kinetic energy. Even though the bullet doesn't weigh very much, it's moving very rapidly. A bowling ball is moving at a much slower speed than our bullet, but it is much more massive. So the bowling ball also has a huge amount of kinetic energy. The other type of energy is called potential energy, which is commonly referred to as stored energy. Potential energy is not as obvious. An object can be sitting at rest and not doing anything in particular, but still contain a huge amount of stored or potential energy. The energy in an object can be stored in a number of different ways. Probably the most important one for us is chemical potential energy. Chemical energy is stored in the chemical bonds in various chemical compounds, and that energy can be released in chemical reactions where bonds are being broken and formed. One of the most important types of chemical potential energy is fuel. So whether it's gasoline, natural gas, propane, wood, or coal, all of these materials contain a large amount of chemical potential energy, and that energy can be released by burning or by combustion. Of course, equally important, or more so really for us, is food. Food has a lot of stored chemical potential energy. Does anybody know the units that we use to measure the chemical potential energy in food? Yes, it's calories. So the number of calories in a particular food item is simply the amount of chemical potential energy stored in that particular food. Now, batteries, you might think, would be electrical potential energy, and that is one of the types of potential energy. But in reality, batteries don't contain any electricity at all. If you cut open a battery, you won't get shocked because there's no electricity in that battery. What there are chemical compounds, and when you connect the two terminals of the battery, a chemical reaction will occur, and it will produce electricity. Does anyone happen to know what kind of chemical reaction produces electricity? And the answer, of course, is a redox reaction. Redox reactions involve the gain and loss of electrons. The key in a battery is that the chemical that's losing and the chemical that's gaining electrons are separated from each other, and the only way the electrons can get from one point to the other is to travel through an external wire, through whatever device the battery happens to be powering. Another type of potential energy is gravitational potential energy. Gravity makes things want to fall from a higher point to a lower point. So anything that has the ability to fall from a higher elevation to a lower elevation has gravitational potential energy. We use that a lot in the United States to generate electricity. Hydroelectric dams hold water, and that water is allowed to flow downhill, and as it flows downhill, it spins turbines on large generators to produce electricity. An avalanche. There's been a lot of avalanches this winter throughout the California and Colorado, and an avalanche, basically the snow is at a high elevation and it wants to go to a lower elevation, so that snow has a lot of gravitational potential energy. A cuckoo clock, not all of you may be familiar with a cuckoo clock. They're the ones with the little bird that pops out once an hour and says cuckoo. But those clocks are powered by weights. Those large black weights you see hanging under the clock, gravity makes those slowly fall, and as those weights fall, they spin the gears inside the clock and make the hands move. When the weights get low, you simply pull them back up again, giving them more gravitational potential energy, and the clock will continue to run. The most powerful source of potential energy is nuclear potential energy. And as the name implies, nuclear potential energy is stored in the nucleus of the atom. I mentioned earlier that chemical potential energy is stored in the bonds in chemical compounds. And nuclear potential energy is stored in the bonds in the nucleus, those bonds connecting the neutrons and the protons. The bonds in the nucleus are millions of times stronger than chemical bonds, which is why nuclear potential energy is millions of times stronger than chemical potential energy. The greatest source of nuclear potential energy we have is the sun. The sun is basically a giant nuclear reactor. The sun is continually converting hydrogen into helium, and as it does so, it releases an enormous amount of energy, which heads out into space, and a small amount of that energy hits the Earth, and we use that energy to make plants grow. We eat the plants, so most of our energy indirectly comes from the sun. We also use nuclear power plants. This is a picture of 3 Mile Island. None of you are probably old enough to remember that, but back in 1979, they had a nuclear disaster there, but luckily, all of the material was enclosed in a large concrete dome, and it kept the radiation from escaping, unlike what happened in Chernobyl a few years later. And of course, nuclear weapons, the bad side of that coin, unfortunately, is we can use nuclear power to benefit mankind by producing electricity, but it also makes a very terrible weapon. Elastic potential energy, sometimes called mechanical potential energy, has been around for a very long time. A lot of kids' toys are powered by that. Anything that you can stretch or twist or bend, and it wants to unstretch and untwist and unbend, has elastic potential energy. For example, a mousetrap. When you set the mousetrap, you're bending that spring, and that spring wants to snap back, so it has elastic potential energy. One of my favorite toys as a kid, back in the days before video games, were these rubber band powered balsa wood airplanes. They were so much fun. You'd wind that rubber band up, storing elastic potential energy, and then it would power the propeller, and those planes would fly all over the place. And of course, more recent toys for my kids were the Nerf guns. They have springs in them, and when you pull those springs back, they get a lot of elastic potential energy. And of course, they want to pop back into their original form and launch those little Nerf darts. The last type of potential energy is electrical potential energy. Now, we said earlier that batteries don't actually store electricity, but it is possible to store electricity directly. Probably the example you're most familiar with is lightning. Lightning is basically static electricity. So that the charges build up on the clouds, and eventually they have to balance each other out with the ground, and so the lightning travels between the clouds and the ground to balance those huge electrical charges. And of course, you've probably encountered static electricity as well. This is particularly common back in the Midwest. When I was a kid, again, back in the Midwest, when it gets really cold and dry, that's when static electricity is at its best. And so we used to have a lot of fun in the wintertime when it would get very dry and cold, and you could really make your hair stand on end. And finally, for you Back to the Future fans, let's go all the way back to 1985 and the famous flux capacitor. A capacitor is basically a device that stores electricity. It's a real thing. I mean, the flux capacitor, of course, was a bit of science fiction, but most electrical devices, your cell phones, any computer, your televisions, they all contain capacitors to store electricity. It's possible, and actually quite common, to convert one form of energy into another. You can change various kinds of potential energy into other types of potential energy, and you can also go back and forth between kinetic and potential. So for example, consider a coal-fired power plant. We start out with coal, which has a lot of chemical potential energy. You burn that coal, and that chemical potential energy is turned into thermal energy, which is basically just the kinetic energy of fast-moving atoms and molecules. The heat from the coal is used to boil water and convert it to steam. So the steam basically has more thermal energy or kinetic energy than the original water. The steam is then used to spin a turbine. So the kinetic energy of the steam is converted to the kinetic energy of this moving turbine, and the moving turbine then produces electricity. And electricity is really a form of kinetic energy as well. The electricity coming out of your electrical outlets at home is simply electrons moving at a very high rate of speed. And it's those fast-moving electrons, it's their kinetic energy that powers your various devices. Now we can finish this up by going full circle and going back to chemical potential energy. If you use the electricity to charge your cell phone battery, you're basically carrying out a chemical reaction inside that battery. So we've gone from the chemical potential energy in the coal through all these various changes, and now we're back to the chemical potential energy of the battery. The downside of all of this, of course, is that every time you convert one form of energy to another, you lose energy, sometimes a significant amount. So the energy of the coal, by the time you get to your cell phone, you've lost a large percentage of that energy you had initially. So it's always good to have as few of these transformations as possible. It turns out that not only can one form of energy be converted into another, but matter can actually be converted into energy, and vice versa. Because mass and energy are basically two forms of the same thing. Einstein was the first person to figure this out from his theory of relativity when he came up with his famous equation E = mc squared, which I'm sure all of you have heard of at one time or another. So in his equation, E is the amount of energy that you can get, m is the mass of the material that's being converted to energy, and c is the speed of light, which we square. How much energy is needed to power the entire Earth for 1 year? Well, we would have to burn 24 billion tons of coal. Or if we used nuclear power, we would only need 7,000 tons of uranium. But if we could somehow convert matter directly into energy, it would only take 7 tons of matter. You could put that easily in the back of a semi-trailer and a truck, and that would be enough material to power the Earth for an entire year. The problem is it's very difficult to change matter directly into energy. It can be done, but only on a very small scale. The only place I know that it's ever been done on a large scale is on one of my all-time favorite TV shows, which is Star Trek, because the power source of the various incarnations of the Starship Enterprise all were based on converting matter directly into energy by using something called antimatter. But that's a story for another day.